Alright, welcome to what I can confidently say are good choices. I'm gonna do a mic check. Mic check 1, 2, looks okay. Oh, so we do have some fuzz on the line. It looks like that could be a problem. Not sure what's happening there. Not sure how to fix that either. Okay, so let's try fixing that. Okay, so maybe this is a little better. Alright, well it's down to like negative 55, so hopefully it's not gonna be as big of a problem. Really not sure what's going on there. But all right. So yeah, hopefully that's not too big of an issue. We're gonna do an LPIC video. That's why I can confidently say this is a good choice. All right. Well, I just think LPIC makes a lot of sense. Um, Let me try pausing it and unpausing it because sometimes it magically goes away when I do that. All right. I'm not sure what's going on. Hopefully it's quite enough. It looks like it hangs around down in this area, so hopefully that's good enough. So yeah, so we're gonna be moving on to the part two of 401 lesson one. So this is a rough one. This is very tedious. We're learning about creating partitions and file systems. So file systems, that's especially a tricky subject. This is a topic about devices, Linux file systems, file system hierarchy standards. So really meaty, beefy concept. So let's waste no time and let's get started. Okay, so creating an ex2 slash ex3 slash ex4 file system. The extended file system, ext, was the first file system for Linux, and through the years was replaced by new versions called ext2, ext3, and ext4, which is currently the default file system for many Linux distributions. The utilities mkfs.ex2, mkfs.ext3, and mkfs.ext4 are used to create ext2, ext3, and ext4 file systems. In fact, all of the these utilities exist only as symbolic links to another utility called MKE2FS. So MKE2FS alters its defaults according to the name it is called by. As such, they all have the same behavior and command line parameters. The most simple form of usage is mkfs.ext2, and then you feed it a target, where target is the name of the partition where the file system should be created. For example, to create an ext3 file system on /dev/sdb1, the command would be mkfs.ext3 /dev/sdb1. So you feed it the name of the partition where you want the file system should be created. So you really got to understand these different concepts. You got to understand what a partition is, what a file system is, what a hard disk is. These are all things within things. So like, and then you can see it from what you feed it in. So the first thing we have here is the disk, then we have the partition, and then we create the file system. We're gonna go with ext3 for some reason in this example, even though the default is 4. Yeah. Alright, so instead of using the command corresponding to the file system you wish to create, you can pass the -t parameter to mke2fs, followed by the file system name. For example, the following commands are equivalent: and we'll create an ext4 file system on dash slash dev slash sdb1. All right, so we've got mkfs, so make file system dot ext4. So that's one way to do it, and then you feed it the partition where you want to make the file system, or you can just do so mkfs is basically like a no, they mentioned this uh yeah, so mk in fact yeah, so these utilities here are just symbolic links to mke2fs. So you can call this here using this syntax, or if you just are comfortable using this, you don't need a shortcut. Then you got to pass it the dash t for the file system. So it probably stands for table or something like that. Um, so you need one, two, three, four things, but you can just do it in two. Separated by a space if you do use the shortcut. But if you don't want the shortcut, then it's mke2fs space dash t space ext4 space and then the partition slash dev slash sdb1. But there's a handy way to make it a bit simpler: mkfs.ext4 space and then your partition. A bit simpler there. All right, so for example, the following commands are equivalent, and we'll create an ex4 file system on this partition. Command line parameters. mke2fs supports a wide range of command line parameters and options. Here are some of the most significant ones. All of them apply to mkfs.ex2, mkfs.ex3, and mkfs.ex4. So the first one, and these apply to all of these, is dash b, which is the size, and this sets the size of the data blocks in the device to what you specify, which can be 1024, 2048, or 4096 bytes per block. Dash lowercase c checks the target device for bad blocks when creating the file system. You can run a thorough but much slower check by passing this parameter twice, as in dash t dash c targets. So you can check the target device for bad blocks in a briefer way where you don't quite get as many as there are, but you can save a lot of time, or in a more thorough way where you get them all, but it costs more time. I'm curious about this here, so let's ask the AI about this. So let's ask, like, so tell me why I would choose 1024, 48, or 4096. The pros and cons of each choice. The pros and cons of each choice, and the situations where there are obvious best choices in this regard, and the situations where it's tricky to make the right choice in this regard. Okay, so yeah, I just want to hear all of this. It's going to be quite a bit, but I think it'll be useful.
Choosing the appropriate block size, also known as the block size or block size, when creating a file system using tools like MKE2FS can significantly impact the performance and storage efficiency of your file system. Each block size has its own set of pros and cons, and the best choice depends on your specific use case. Here's a breakdown of the common block sizes: 1024, 2048, and 4096, and their considerations. 11024 bytes per block asterisk. Pros asterisk. Smaller block sizes can be beneficial for small files since they reduce internal fragmentation. This means that smaller files won't waste as much space. Better for file systems with many small files. Cons asterisk. Inefficient for large files as it can lead to significant metadata overhead and reduced read/write performance. More blocks mean more metadata, which can increase the overhead and decrease overall storage efficiency. Best use cases asterisk. Ideal for systems with predominantly small files, such as a mail server or a web server with many small HTML or text files. 220-48 bytes per block asterisk.
This is probably what most of
Pros
them are.
asterisk. A middle ground choice that offers a compromise between small and large block sizes. Suitable for a wide range of use cases, balancing efficiency for
Yeah,
both
general
small and
purpose.
large files. Cons asterisk. May still have some inefficiency with very small files but is generally more balanced. Best use cases asterisk. Recommended for general purpose file systems where the file sizes vary widely.
Yeah, I'm sure most are like that.
340-96 bytes per block asterisk. Pros asterisk. Efficient for larger files and minimizes metadata overhead. Offers better read/write performance for large files. Cons asterisk. Less efficient for small files due to increased internal fragmentation.
Oh, this is a good
Best
one.
use cases asterisk. Best suited for file systems with predominantly large files,
That's good
such
to
as
know.
media servers, databases,
I've been
or
thinking
data
about getting a
storage
media
systems.
server.
Tricky considerations asterisk. Mixed workloads asterisk. If your file system contains a mix of small and large files, choosing the right block size becomes challenging. In such cases, you might need to strike a balance or consider using a utility like Tune2FS to change the block size after the file system is created. Storage efficiency versus performance asterisk. The trade-off between storage efficiency and performance is crucial. Smaller block sizes are more storage efficient for small files but can lead to lower performance for large files. Larger block sizes are better for large files but less efficient for small ones. Compatibility asterisk. Consider compatibility with other systems or applications that might expect a specific block size. Changing block sizes after creating a file system can be complex and potentially risky. In conclusion, the choice of block size depends on your specific use case and the types of files you'll be working with. There's no one-size-fits-all answer, and you may need to analyze your workload and performance requirements to make an informed decision. In some cases, a middle ground choice like 2048 bytes per block may be the most practical option.
Okay, so yeah, that makes a lot of sense. It's kind of like, you know, network traffic in a way. Like, for calls and videos, you want there to be like UDP, smaller frame sizes, so that like when you lose something, you're not losing as much at a time. Um, and you have a more a process where, yeah, you just want there to be very low latency, and then you want any kind of frame loss to be a very small portion of what is being sent. So it's kind of similar when considering file system block sizes. For really small block sizes, that's going to be like emails. So like an email server, even like a web server if you're not really hosting any like big videos or anything on it. So yeah, so that makes sense. And then where it's really important, I think, to know is like if you have like a home media server or something like that. I don't have that yet, but that's definitely gonna be on my radar very soon. I'm sure. So like you would use the big block size because movies I'm sure are like pretty big. So you want a big block size for that. So yeah, that was super helpful. All right, so we learned about dash C already. So dash D is the next one, and then you feed it a directory. It copies the contents of the specified directory to the root of the new file system. Useful if you need to pre-populate the disk with a predefined set of files. The next one is dash uppercase F. Danger Will Robertson. We can do that. Let's take a look at the actual. Oh yeah, it's 5 minutes. Yeah, here we go. Or 5 seconds. I mean. Oh, it's not. Let's.
Danger, Will Robinson.
There we go.
Danger,
There we go.
no, Will Robinson.
That's what I'm looking for. So this option will force MK2FS to create a file system, even if the other options pass to it or the target are dangerous and make no sense at all. So you can make an arbitrary file system that makes zero sense and doesn't even work if you use -F. If specified twice, as in -F space -F, it can even be used to create a file system on a device which is mounted or in use, which is a very, very bad thing to do. So I guess that could be kind of like a self-destruct button. So like if you've got compromising videos of yourself on a drive, then you can do what is it? MKE2FS -F and then pass other options to it that would like just make it not make any sense. And you might get, maybe there'll be a frame or two of your bare naked ass out there on the internet, but the full video will be lost. All right, so -L and then volume label will set the volume label to the one specified in volume_label. This label must be at most 16 characters long. Okay, and then -n. This is a truly useful option that, oh thanks, that none of them else were useful. That simulates the creation. Oh, it's kind of like a check mode. It's kind of like an Ansible, check mode in Ansible, or like a commit check in Juniper Gears. So yeah, that's truly useful. Truly useful option that simulates the creation of the file system and displays what would be done if executed without the -n option. Think of it as a trial mode. Good to check things out before actually committing any changes to the disk. So I think I need to do this, to be honest, because I have other drives for my lab, and I can close my server there. But I've been trying to put other drives into my home lab, and like I've been having trouble doing that, and I think it's because and I think as a result of learning about this LPIC, I should be able to fix that, because we can see right here, like I just have SDA in there, so like I want to add an SDB, an SDC, like I want to add as many drives to it as I can so that I can have more storage space in my lab. Like anytime a laptop fails, the first thing I want to be able to do with that laptop is pull out that drive and plug it into my home lab. So we'll try that later, but right now let's just keep going. So yep, good to check things out before actually committing any changes to disk. Definitely is the case. So next is -q, which stands for quiet mode. MKE2FS will run normally, but will not produce any output to the terminal. Useful when running MK2FS from a script. The next one is -U and then the ID, the unique universal identifier, or universally unique identifier, I mean, is what you feed to it here. So it's that long, super long string. Yeah, like here's an example of it down there. So this will set the UUID, universal unique identifier, of a partition to the value specified as ID. UUIDs are 128-bit numbers in hexadecimal notation. So does that sound familiar? It's basically like a IPv6 address, right? Um, that serve to uniquely identify a partition to the operating system. This number is specified as a 32-digit string in the format. Yeah, it's just in a different format. IPv6 addresses, I think, are in the format uh, uh, um, 8, 8, and 8, and then this will be an 8, and then these are split. So it's in this format 8, 8, 8, and 8. Let's look at an IPv6 address quick, because IPv6, if you're like me in North America, you learn all about it, and then you don't really use it that much. So it's easy to forget. Um, all right, so IPv6, uh, they're not being clear about. This is a bad. Yeah, I don't like this page. I just want to see some. Maybe this one's good. This is from Cisco. Uh, yeah, here we go. So it's 128-bit addressing. Now let's see what the format is, if we can get that from here. Like, I want to see an actual. Oh, here we go. So if we go to. Uh, so I mean, the thing is it's just like a. So it uses hexadecimal digits. Uh, and each, yeah, just like before. But what I want to know is what is the format? So we know that UUIDs are in the format of they're separated by dashes. So this is the number of characters, 8 characters dash 4 characters dash 4. So what is the format of IPv6? Is it 8 8 8 and 8 separated by dashes? Is it what I think it is, just off the top of my head, 8 8 8 and 8? Actually, it's 4 4 4 4, and then 4 4 4 4, separated by colons. I think that's what it is. Yeah, so like, yeah, that's what it is. 1 2 3 4 5 6 7 8. So it's 4 4 4 4 4 4 4 4, and each set of fours is separated by colons. I remember now. And then there's abbreviation techniques that make it so that's not completely insane. It looks like there's no such abbreviation techniques for UUID, so anytime you get an UUID, it's going to be pretty unwieldy like this. IPv6, those abbreviation techniques make it not too bad. But you can think of it like an IPv6. That might be a good way to remember how many bits there are. You just got to remember that format. Sometimes it's tricky. So the format is 4 4 4 4, and then another set of 4, and then the divider is colons instead of hyphens. So this number is specified as a 32. Yeah, so UUIDs are 128-bit numbers in hexadecimal notation, just like IPv6 addresses, that serve to uniquely identify a partition to the operating system. This number is specified as a 32-digit string. Yep, 32-digit string with each digit being a hexadecimal character in the format of 8 characters. So we can see down here, we've got 8 characters, and then a hyphen, and then 4 characters, hyphen, 4, hyphen, 4, hyphen, and then 12 at the end. Meaning 8 digits, a hyphen, 4 digits, a hyphen, 4 digits, a hyphen, and 4 digits, a hyphen, and then 12 digits. And digits I don't like. It should say characters. It should be hexadecimal characters, not digits, because A through F, which is a part of which are valid hexadecimal characters, they're not digits. So they're not numerical digits. They're alpha, you know. So I don't like this word digit here, but let's keep going. So like, and then here's the example. Instead of an ID, you can also specify parameters like clear to clear the file system UUID, random to use a randomly generated UUID, or time to create a time-based UUID. So let me do one thing. I do want to ask the AI something. And what I want to ask it is, so when it says meaning 8 digits hyphen 4 digits and so on, is the word digits kind of inappropriate to use here? Would it be better to call them characters, or even better, hexadecimal characters? Because 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 isn't A through F not technically a digit, but those are going to be those are valid characters in a UID? Let's see what the AI says about that. Yeah, valid point.
So when it says meaning 8 digits, hyphen, 4 digits, and so
Oh,
on,
that's the wrong thing. Okay, there we go.
You raise a valid point. The term digits in the context of a UUID can be somewhat ambiguous
So be
because it may
careful
imply
to
decimal digits,
understand.
0 to
Yeah.
9, while in reality, UUIDs are in hexadecimal notation, which includes not only decimal digits but also the letters AF, 0 to 9, AF. Therefore, it would be more accurate and clear to refer to them as hexadecimal characters
Right.
or simply characters when describing the components of a UUID. So, the sentence could be improved to say: the format of a UUID is described as a 32-character string separated by hyphens,
Exactly.
8-4-4-4-12, dot.
Thank you.
This terminology is more precise and avoids potential confusion regarding the use of the term digits.
I love being validated. It's much better than being ignored or discounted. Okay, so yeah, there we go. Instead of an ID, you can also specify parameters like clear to clear the random or time. Read that already. So the next is dash capital V, which is verbose mode. It prints much more information during operation than usual, and it's useful for debugging purposes. So okay, so next let's see what we're at. Oh, we're only at 28. Let's see how much is left to go. I think there's quite a bit left to go, but okay, yeah. So we'll do at least this section. I do need to take a break, so I'm going to take a break right now, and I'll be right back. All right, I'm back. So let's keep going. Next section is creating an XFS file system. All right, so XFS is a high-performance file system originally developed by Silicon Graphics in 1993, cutting edge, for its IRIX operating system. Due to its performance and reliability features, it is commonly used for servers and other environments that require high or guaranteed system bandwidth. Tools for managing XFS file systems are part of the XFS PROGS package. This package may need to be installed manually, as it is not included by default in some Linux distributions. Others, like Red Hat Enterprise Linux 7, Use XFS as the default file system. XFS file systems are divided into at least two parts: a log section, where a log of all file system operations, commonly called a journal, are maintained, and the data section. The log section may be located inside the data section, the default behavior, or even on a separate disk altogether for better performance and reliability. The most basic command to create an XFS file system is mkfs.xfs space target, where target is the partition you want the file system to be created in. For example, mkfs.xfs space /dev/sda1 is the partition. As in MKE2FS, mkfs.xfs supports a number of command line options. Here are some of the most common ones. So dash lowercase b size equals value. So you got to set it to a value. Sets a block size in the file system in bytes to the one specified in value. The default value is 4096, so that's the highest option we had before. The minimum is 512, and the maximum is much higher than we had before. It's 65536. So let's go back and look at the maximum. So the maximum was only 4096. This is now the default, and the maximum is much, much higher than that. So the next one is dash lowercase m, and then crc equals a value. Parameters starting with lowercase m are metadata options. This one enables if value is 1 or disables if value is 0. The use of crc32c checks to verify the integrity of all metadata on the disk. This enables better error detection and recovery from crashes related to hardware issues, so it is enabled by default. The performance impact of this check should be minimal, so normally there is no reason to disable it. The next option is dash lowercase m, UUID equals, and then you feed it a value. Sets the partition UUID to the one specified as value. Remember that UUIDs are 32 character 128 bits, like an IPv6 address, numbers in hexadecimal base, group specified in groups 8, 4, 4, 4, and 12, and then they say digits, but they're actually hexadecimal characters separated by dashes, like we see there in the example. The next one is dash lowercase f, which stands for force the creation of a file system on the target device, even if a file system is detected on it. Then dash lowercase l log dev equals a device. This will put the log section of the file system on the specified device instead of inside the data section. I'll do a mic check 1 2. It's a bit quiet. I guess I'll talk closer to the mic. The white noise is still kind of bad, but alright. So next one is dash lowercase l, size equals value. This will set the size of the log section to the one specified in value. The size can be specified in bytes, and suffixes like lowercase m or lowercase g can be used. Dash l size equals 10m, for example, will limit the log section to 10 megabytes. Let me just try something quick. Sometimes there's a cable that comes loose. Okay, that didn't do anything. Alright. So the next one is dash uppercase L and then feed it a label. Sets the file system label, which can be at most 12 characters long. Then dash uppercase n, similar to the lowercase n parameter of MKE2FS, will make mkfs.xfs print all the parameters for the creation of the file system without actually creating it. Alright, so the next section is creating a FAT or VFAT file system. The FAT file system, FAT, all in uppercase, originated from MS-DOS and through the years has received many revisions culminating on the FAT32 format released in 1996 with Windows 95 OSR2. VFAT is an extension of the FAT16 format with format for long up to 255 characters file names. Both file systems are handled by the same utility. mkfs.fat, mkfs.vfat is an alias to it. The FAT file system has important drawbacks which restrict its use on large disks. FAT16, for example, supports volumes of at most 4 gigabytes. Ooh, that's pretty bad. And a maximum file size of 2 gigabytes. Wow, good luck playing Witcher 3 on that. FAT32 ups the volume size to up to 2 petabytes. There we go, now we're talking. And the maximum file size to 4 gigabytes. Because of this, FAT file systems are today more commonly used on small flash drives or memory cards up to 2 gigabyte in size, or legacy devices and OSs that do not support more advanced file systems. So I have a question about that. So then why not use the better ones? So why use the FAT system for small flash drives? Why not just use the best and most modern file system, even though the drive is small? Are modern file systems not able to handle small drives?
Using the FAT file system for small flash drives is a matter of compatibility and practicality, and it doesn't necessarily reflect the inability of modern file systems to handle small drives. Here are some reasons why the FAT file system is still commonly used on small flash drives. 1. Compatibility. FAT file systems are widely supported across various operating systems, including Windows, Mac OS, Linux, and many embedded systems. This means that a flash drive formatted with FAT can be used on a broad range of devices without any compatibility issues. If you want to share data between different computers and devices, especially older or less common ones, FAT is a safe choice.
Makes a lot of sense.
2. Simplicity. FAT is a simple and well-documented file system. It has minimal overhead, which means that it doesn't consume much storage space on the drive itself. This is important for small drives with limited capacity. Modern file systems like NTFS or ext4 have more features and can be less space efficient on small drives. 3. Ease of use. Formatting a drive with FAT is straightforward and doesn't require specialized tools or software. It can be done directly through the operating system's built-in formatting tools. This ease of use makes it accessible to a wide range of users. 4. Legacy compatibility. As mentioned in the original content, there are still legacy devices and operating systems in use today that do not support more modern file systems. If you need to use a small flash drive with such devices.
Oh, it just kind of stopped reading. But I mean, I get the gist of it. Yeah.
Using the FAT file
Oh,
system
sorry.
for small flash.
I get the gist of it. It makes sense. Okay, so yeah, so the most basic command for the creation of a FAT file system is mkfs.fat space target, where target is the partition you want the file system to be created in. For example, dash slash dev slash sdc1. Like other utilities, mkfs.fat supports a number of command line options. Below are the most important ones. A full list and description of every option can be read in the manual for the utility with the command man mkfs.fat. So we've got the option dash lowercase c, which checks the target device for bad blocks before creating the file system. Then dash uppercase C, and you have to feed it a file name and a block count. We'll create the file specified in file name, and then create a FAT file system inside it, effectively creating an empty disk image, which can be later written to a device using a utility such as DD or mounted as a loopback device. When using this option, the number of blocks in the file system, block count, must be specified after the device name. Dash uppercase F, and then the size. Selects the size of the FAT file allocation table between 12, 16, or 32. For example, between FAT12, FAT16, or FAT32. If not specified, mkfs.fat will select the appropriate option based on the file system size. Then the next option is dash lowercase n, as in name. And then you feed it the name. It sets the volume label or name for the file system. This can be up to 11 characters long, and the default is no name. Then the next option is dash lowercase v, which stands for verbose mode. And it prints much more information than usual, which is useful for debugging. Alright, so take a note. mkfs.fat cannot create a bootable file system. According to the manual page, this isn't as easy as you might think and will not be implemented. Okay, well that's interesting. I wonder what so what are bootable? So what file systems are bootable? Let me ask the AI that. So what file systems are bootable? And how were they able to accomplish this feat if it isn't as easy as you might think? This is a long one. Let's do it.
Bootable file systems are specific types of file systems that contain the necessary files and configuration to start an operating system or boot a computer. The ability to create a bootable file system involves several factors, including the file system structure, bootloader configuration, and potentially other elements like kernel images and device drivers. Some commonly used bootable file systems include 1. FAT, File Allocation Table. FAT file systems, such as FAT16 and FAT32, are often used for bootable partitions on USB drives and memory cards. They are relatively simple and widely supported, making them suitable for this purpose. 2. NTFS, New Technology File System. NTFS is the default file system for Windows
Alright, I'm not going to listen to all that. I think it's saying that... Okay, so let me understand this. In the initial text I highlighted, did they mean that although FAT is a bootable file system, that although it is, when you use the tool mkfs.fat, you only have the ability to create a FAT file system that is not bootable, despite the FAT file system having the ability to be bootable, is what they meant that creating a command line utility to make a bootable FAT file system isn't as easy as you'd think, despite FAT having the capacity to be bootable. Is that what they mean?
Yes,
oh, okay, yeah.
You've understood the statement correctly.
Good.
In the initial text you highlighted, it means that although FAT is a file system format that can be used for bootable partitions, when you use the specific command line utility mkfs.fat, it may not have the capability to create a FAT file system that is bootable. The statement is essentially saying that mkfs.fat might not provide the necessary features or configurations to create a bootable FAT file system. So, what they meant is that creating a command line utility like mkfs.fat to make a bootable FAT file system isn't as easy as one might think, despite the fact that FAT itself has the capacity to be bootable. The difficulty likely lies in the complexities of configuring the file system correctly for booting, including setting up the boot sector, specifying the bootloader location, and ensuring the necessary boot-related files are present and correctly referenced within the file system.
Like you're dealing with the BIOS and UEFI. So yeah, I can imagine it being difficult. All right, so let's move on to creating an exFAT file system. I'll do another mic check 1 2. Looks good to me. So exFAT is a file system created by Microsoft in 2006 that addresses one of the most important limitations of FAT32, file and disk size. On exFAT, the maximum file size is 16 exabytes. Now we're talking, from 4 gigabytes on FAT32. Good improvement. And the maximum disk size is 128 petabytes. All right. As it is well supported by all 3 major operating systems, Windows, Linux, and Mac OS, it is a good choice where interoperability is needed, like on large capacity drives, memory cards, and external disks. In fact, it is the default file system as defined by the SD Association for SDXC memory cards larger than 32 gigabytes. And that's the exFAT file system. The default utility for creating exFAT file systems is mkfs.exFAT, which is a link to mkexfatfs. The most basic command is mkfs.exFAT space target, where target is the partition you want the file system to be created in. For example, mkfs.exFAT space /dev/sdb2. Contrary to the other utilities discussed in this lesson, mkfs.exFAT has very few command line options. They are -i, vol ID sets the volume ID to the value specified in vol ID. This is a 32-bit hexadecimal number. If not defined, an ID based on the current time is set. Dash lowercase n and then name sets the volume label or name. This can have up to 15 characters and the default is no name. Dash lowercase p and then sector. You pass the sector to it. Specifies the first sector of the first partition on the disk. This is an optional value and the default value is 0, but you can set it to whatever you want. And then dash lowercase s, which stands for sectors. As opposed to sector, you use dash p for one sector, you use dash x for sectors. Defines the number of physical sectors per cluster of allocation. This must be a power of 2, like 1, 2, 4, 8, and so on. Alright, so next section is getting to know the BTRFS file system. And yep, moving right along here. So BTRFS, officially the B-tree file system, pronounced as ButterFS, BetterFS, or even Butterfuss. Your pick. I guess I'll call it BetterFS because it's BTR stands for better, so BetterFS is a file system that has been in development since 2007. Wow, okay. Specifically for Linux by the Oracle Corporation, I've heard of that, and other companies including Fujitsu, Red Hat, Intel, and SUSE. Heard of that as well, among others. That's interesting. I would love to develop a file. Why is it so hard to develop a file system? I'm curious about that. Why is it so hard to develop a file system? Why are these big companies still working on it since 2007? Why hasn't some nerd in his mother's basement done this yet? All right, yeah, let's hear about it. This is interesting.
Developing a file system is a complex and challenging task for several reasons. 1. Data integrity and reliability. One of the primary goals of a file system is to ensure the integrity and reliability of stored data. This involves handling issues such as preventing data corruption, recovering data in case of failures, and managing data efficiently. 2. Compatibility. File systems need to be compatible with existing software and hardware ecosystems. Ensuring compatibility with various operating systems, hardware configurations, and use cases can be a daunting task. 3. Performance. File systems must be designed to provide efficient data access and storage. Achieving high performance levels requires optimizing algorithms, data structures, and I/O operations. 4. Security. Security is a top priority in file system design. Protecting data from unauthorized access and ensuring data privacy is a complex endeavor. 5. Scalability. File systems must be scalable to handle large volumes of data. This includes designing data structures and algorithms that can efficiently manage data growth. 6. Maintenance and support. Ongoing maintenance, updates, and support are essential for a file system's longevity. As technology evolves, file systems must adapt to new requirements and challenges. As for why companies like Oracle, Red Hat, Intel, and others have been working on BTRFS since 2007, there are several reasons. 1. Industry-driven. These companies have a vested interest in improving Linux and its file systems because they rely on Linux for various products and services. Contributing to file system development helps ensure the platform's reliability and performance. 2. Complexity. The complexity of developing a file system means that it takes time to refine, test, and optimize. Incremental progress is often made over many years. 3. Quality assurance * developing a robust file system requires extensive testing and validation. This process helps identify and fix potential issues, ensuring data safety and system stability. 4. Evolving needs * computing environments and requirements continually evolve. Ongoing development allows file systems like BTRFS to adapt to changing needs and incorporate new features. 5. Community involvement * many file systems, including BTRFS, have active open source communities that contribute to their development. These communities bring together
Okay,
expertise from
so
various individuals,
because those people are
including those
working
who
on it.
might be nerds in their mother's basements, to collectively enhance the file system. While individuals working independently on file systems have made contributions, developing a file system that meets the rigorous standards of modern computing and is suitable for widespread use is a complex undertaking. It often requires the resources, expertise, and collaboration that larger organizations can provide. However, open source projects like BTRFS do benefit from the collective
Oh, this is
efforts
open
of a wide
source.
range of contributors, not just those in corporate environments.
Oh, that's cool. So there are many features that make better FS, better file system attractive on modern systems where massive amounts of storage are common. Among these are multiple device support, including striping, mirroring, and striping and mirroring, as in a RAID setup, transparent compression, SSD optimizations, incremental backups, snapshots, online defragmentation, offline checks, support for subvolumes with quotas, deduplication, and more. As it is a copy on write file system, it is as it is a copy on write file system, it is very resilient to crashes. That sounds good to me. And on top of that, BetterFS is simple to use and well supported on many Linux distributions. And some of them, like SUSE, use it as the default file system. Let's do a Google search for BetterFS because they said it was open source. Oh. I don't see it like on GitHub or whatever, but we do have Arch Linux has it here. Okay, so yeah, there's some good stuff written about it. Alright, so note. On a traditional file system, when you want to overwrite part of a file, the new data is put directly over the old data it is replacing. A copy on write file system. So on a copy on write file system, the new data is written to free space on the disk. Then the file's original metadata is updated to refer to the new data, and only then the old data is freed up as it is no longer needed. This reduces the chances of data loss in case of a crash, as the old data is only discarded after the file system is absolutely sure that it is no longer needed and the new data is placed. So if you're a data scientist, if you're working on cutting edge physics, definitely use this. You don't want to lose your data. If you're a politician or a Hollywood actor or actress, don't use this file system. just don't. Alright, so creating a BTRFS, a BetterFS file system. So the utility mkfs.betterfs is used to create a BetterFS file system, BTRFS. Using the command without any options creates a BetterFS file system on a given device like so. So here we go. So it's mkfs.btrfs space, then the partition, which is /dev/sdb1. Tip: if you do not have the mkfs.btrfs BetterFS utility on your system, look for BetterFS-progs in your distributions package manager. I'm not following along with these because, like, it's a big deal to change the file system on your partitions. So, like, and to create new partitions to delete them. I'd want to do that on like a safer disk. Right now I only have the one disk working in my lab, so if I could get another disk to work, I'd do that on that one. But that's why I'm not doing this on my lab or any of my stuff, because I don't want to blow away my data. All right, so you can use the -L to set a label or name for your file system. BetterFS labels can have up to 256 characters, except for new lines. So I guess new lines do not count. I'm confused. Oh no, when you set a label for your file system, you can't include new lines in the labels. It all has to be on one line. So here's an example of that: mkfs.btrfs space the partition, which is /dev/sdb1 space -L space, and then in quotes you wrap the label. It can have spaces, but it can't have multiple lines. All right, so tip: enclose the label in quotes like above. If it contains spaces, you can also use a escape character in bash, which is the \, but yeah, this is the cleanest way to do it. So note this peculiar thing about peculiar thing about BetterFS. You can pass multiple devices to the mkfs.betterfs command. Passing more than one device will span the file system over all the devices, which is similar to a RAID or LVM setup. To specify how metadata will be distributed in the disk array, use the -m parameter. Valid parameters are RAID 0, RAID 1, RAID 5, RAID 6, RAID 10, single, and dupe. For example, to create a file system spanning /dev/sdb1 and /dev/sdc1, concatenating the two partitions into one big partition, use mkfs.btrfs space /d space single space -m space single space /dev/sdb space /dev/sdc. All right, so warning: file systems spanning multiple partitions, such as above, might look advantageous at first, but are not a good idea from a data safety standpoint, which is ironic because RAID, from what I understand, is for data safety. As a failure on a single disk of the array means certain data loss. The risk gets bigger the more disks you use, as you also have more possible points of failure. Okay, so you want a file system per disk. All right, so moving right along, still got quite a bit to get through here. And we're at the hour mark. So next is managing subvolumes. Subvolumes are like file systems inside file systems. You can expect that to happen. We got a lot to go. Think of them as a directory which can be mounted as and treated like a separate file system. Subvolumes make organization and system administration easier, as each one of them can have separate quotas or snapshot rules. Note: subvolumes are not partitions. A partition allocates a fixed space on a drive. This can lead to problems further down the line, like one partition running out of space when another one has plenty of space left. Not so with subvolumes, as they share the free space from their root file system and grow as needed. Suppose you have a BetterFS file system mounted on /mnt/disk, and you wish to create a subvolume inside it to store your backups. Let's call it BKP. So BetterFS subvolume create and then BKB. So slash mount slash disk slash BKP. Next, we list the contents of the slash mount slash disk file system. You will see that we have a new directory named after our subvolume. So ls dash lh and then slash mount slash disk. And we have a new directory here named after our subvolume, which we named BKP, all in uppercase, so we can see it right here. Note, yes, subvolumes can also be accessed like any other directory. We can check that the subvolume is active with the command betterfs subvolume show and then our subvolume. So should see some indicator that it's active. So maybe this one's not active because I don't see any indicator of that. Maybe a flag would show it. I don't know. Or maybe it just wouldn't show up if it weren't active. So you can mount the subvolume on slash mnt slash bkp by passing the -t btrfs -o subvol equals name parameter, where name is the name you give it. In this case, they're going to call it bkp, all in uppercase, to the mount command. So here's the command: mount -t betterfs -o subvol equals uppercase bkp, and then the partition slash dev slash sdb1, and then the subvolume, which is slash mount slash bkp. Okay, so note, the -t parameter specifies the file system type to be mounted. All right, so next section is let's get down here. I think it's possible to get down there. Yeah, we won't be able to finish it all the way out to the questions, but we can get here. Things are going fast. Okay, so working with snapshots. Snapshots are just like subvolumes, but pre-populated and with contents from the volume from which the snapshot was taken. When created, a snapshot and the original volume have exactly the same content, but from that point in time, they will diverge. Changes made to the original volume, like files added, renamed, or deleted, will not be reflected on the snapshot, and vice versa. Keep in mind that a snapshot does not duplicate the files and initially takes almost no disk space. It simply duplicates the file system tree while pointing to the original data. The command to create a snapshot is the same used to create a subvolume. Just add the snapshot parameter after btrfs subvolume. The command below will create a snapshot of the betterfs file system with an N, mounted in slash mount slash disk in slash mount slash disk slash snap. So here we go. We see that command here, betterfs subvolume snapshot. So we're creating a snapshot of slash mount slash disk, and we're going to name it slash mount slash disk slash snap. Now imagine you have the following contents in slash mount slash disk. There we go. We've got a bunch of pictures here. Note the snap directory. You see it right here, containing the snapshot. Now let us remove some files and check the directory contents. So we're removing this LG file. We're removing both of these because we use the glob character there, and then list dash LH in lowercase. Okay, so yep, so now we've got everything without these though. However, if you check inside the snap directory, the files you deleted are still there and can be restored if needed. Pretty handy. If it didn't work that way, it wouldn't quite be so handy. So ls-l for long format, and then -h for the human readable format, we see here, and then we're looking inside this backup we made there, and we see the 2 files that we deleted. It is also possible to create read-only snapshots. They work exactly like writable snapshots, with the difference that the contents of the snapshot cannot be changed. They are frozen in time. Just add the -r parameter when creating the snapshot. Alright, so BetterFS subvolume snapshot -r /mount/disk /mount/disk/snap. Alright, so finishing this up here with a few words on compression. BetterFS supports transparent file compression with 3 different algorithms available to the user. This is done automatically on a per file basis as long as the file system is mounted with the -o compress option. The algorithms are smart enough to detect incompressible files and will not try to compress them, saving system resources. So on a single directory, you may have compressed and uncompressed files together. The default compression algorithm is zlib, all in uppercase, but LZO, all in uppercase, is faster but has a worse compression ratio, or ZSTD, faster than LZIB, comparable compression, are available. So you probably would never want to use LZO, you'd use ZSTD. With multiple compression levels. See the corresponding objective on mount options. Alright, so that's all I got. Yeah, it's well over an hour, which is kind of a good stopping point for these videos. So let me queue it up for the next one. Make sure that this works. Sometimes it's a little finicky to get right. Yep, there we go. So, yep, that's it, and stay tuned for the next video.